Let's move on to something a little different. This is called combinations with repetition. And it's the next section in our textbook. I hope you are reading the text. I don't assume that I'm covering everything in the textbook. Between the stuff that I cover and the text, you should have everything pretty well taken care of. Hey, let's talk about an example here that explains what we mean when we say combinations with repetition. Let's suppose that we have six people that are voting, and with most any case of voting, let's suppose they can say yes, no, or they can abstain. Okay? How many different outcomes are possible when 6 people are voting like this? I mean, they can all vote yes, they can all vote no, and in the end, we just want to know how many yeses there were, how many no's. So order doesn't count. So this is a combination. You know, we just want to know. I mean, for example, if you just need a majority, you just need 4 votes. We don't care who are the 4 that vote yes. We just need to know that we have 4. So this is the case of combinations. Let's think about it this way. If we want to know how many different outcomes are possible, we could set up a table and do something like this: yes, no, and abstain. And we could go ahead and write this all out. Let's suppose that we have 6 yeses. That would look like this. Or we could have 5 yeses and a no. Or we could have 5 yeses and an abstain. We could have 4 yeses and 2 no's. 4 yeses, a no, and an abstain. We could have 4 yeses, nobody saying no, but 2 abstaining. We could sit here and we could write this whole thing down, which is possible because we're only talking about 6 people. But at some point you say, good grief, this could take all day. Imagine if we have 20 people and we were sitting here writing all this out. So, I mean, so far we're down to 3 people saying yes, and then this continues on down, let's think there's got to be a better way to do this. There's 6 people voting. 1, 2, 3, 4, 5, 6. I want you to think about the idea of partitions, dividers, things that, like, you're probably familiar with partitions. A lot of churches now have this big fellowship halls, but then they can pull out these dividers that divide the large room into smaller rooms. If we go with this order of yes, no, abstain, and we have 6 voters, I want you to think with me, what would I be indicating if I put a divider there and a divider there? If we let the first group be the yeses, the second group be the no's, and here would be the abstain, these partitions here would be indicating 2 yeses, 3 no's, and 1 abstain. Well, it only took 2 partitions to divide this into 3 groups. Let's try something else. 2, 3, 4, 5, 6. What if I put 1 partition here and 1 partition there? We have 4 yeses, 2 no's. There's nothing out here. There's nothing to the right of this second Aha. That means that nobody abstained. Okay. We're going to use this idea of partitions. We're going to use this idea of dividers when we're talking about combinations with repetition. The idea of a repetition is that more than one person can choose these different outcomes. We'll do another example with ice cream that I think will drive the point home. But let's stick with votes for now. So we have 6 people, and we have 2 partitions, because to put it into 3 groups, we only needed 2 partitions. So let's think about it. Instead of 6, how about if we go ahead and include the partitions, and where are we going to put the 6 voters if we have 8 positions? Or maybe, how about this? Where would we put the 2 partitions in these 8 positions? Okay, well, here, let's try something. Let's look at this example right here. 3 said yes, 1, 2, 3, partition. Okay, 2 said no, 1, 2, partition, 1 abstained. Oh, look at that. There's room for everybody. So there's voter 1, voter 2, voter 3. There's the partition, voter 4, voter 5, and then voter 6 abstained. So yeah, we found 2 spots to put in the partitions, or we could have chosen 6 spots for the voters. So we're trying to figure out how many different outcomes are possible. Well, when you have 8 spaces, how many different ways are there to choose where you're going to put the 6 voters? Or how many different ways are there to choose where you're going to put the 2 partitions? Okay, so what we ended up here with is, instead of 6, trying to order 6 or 2, what we end up with is we have 6 voters, 3 choices, but we needed only 2 partitions. Okay, and then how many different ways can you choose where you're going to put those 6 voters in those 8 spots? 8 spots, 6 plus 3 minus 1 is 8. Right? Or you could say, well, think about it this way: 6 voters, 3 choices, but we're only going to need 2 partitions. I just want to know where to put the 2 partitions. Okay? Yeah, that's pretty cool. I mean, I think it is, because it's a simple way to figure out how to do these combinations with repetition. You can simplify the problem down by adding the number of items plus the number of groups minus 1, because you need 1 less partition than the number of groups. So we're trying to put these 6 items into 3 groups, so it's going to require 2 partitions. And so there you go. This is going to end up being, if we calculated this out, this is just 8 choose 6, or 8 choose 2. And you know from the symmetry of Pascal's triangle that those are going to give you the same thing. All right, let me get my hand out of the way, but let me suppose that we go with another example. Let's start with a new clean piece of paper, and this time we're going to say you're going to go out with your friends, and so you've got 5 friends including you, and you go over to Cold Stone, and they have 8 flavors of ice cream. Now, I guess Cold Stone's not a very good example because you just make your own flavors there. So you go to UDF or wherever you can get some decent ice cream for a good price. So you have 5 friends, and you have 8 flavors. If we're going to figure out how many different outcomes there are, if your 5 friends, you and your 4 friends, if 5 friends are ordering ice cream from 8 flavors and everybody's just choosing 1 flavor, then we're just going to need 7 partitions. And one of the outcomes could be look something like this. If you have 5 friends and 7 partitions, that's going to be 3, 4, 5, 6, 7. Okay? I want you to think about what this would mean. Let's number your friends 1, 2, 3, 4, 5. And let's put a divider or a partition there, another one there. Don't get all messed up by the fact that there's more partitions, there's more dividers than there are friends. It's not a problem. So remember this, we said there's 8 flavors. Well, here's your first divider, so this is the first flavor. There's nobody between those two, so nobody chose the second flavor.
Nobody wanted the 6th flavor. Nobody wanted the 7th flavor. So what does that leave down here at the end? Friend number 5 chose the 8th flavor. Okay? Again, combinations with repetition, it's okay that these 2 friends chose the same flavor. And obviously, it's okay if some of the flavors were not chosen at all. The point here is that we had 5 friends and they were asked to choose from 8 different categories or 8 different groups, and so we only needed 7 partitions, and we want to figure out how many different combinations how many different ways can you choose those flavors. So you can either, out of this total of 12 spaces, you can say how many different ways can I choose which 5 of the 12 to place my friends, or you can say out of these 12 spaces, where am I going to put the 7 partitions? Okay. Either way you do it, you're going to end up with 5 plus 8 minus 1 factorial over 5 factorial 8 minus 1 factorial. Okay. Either way, that's how you do it.
Sorry about that.
All right. That's it. That's the first 2 examples on combinations with repetition. We will continue to talk about this as we advance in this section, probably in the next class.